we're going to take a look at some of the reactions of nitriles. So once you have them in your molecule, what can you convert them to? The first is a hydrolysis to give a carboxylic acid. And at this point, it's worth mentioning that although it may not seem like it on first glance, the CN group is a carboxylic acid derivative. And just like an ester, an amide, and acid chloride, those are all carboxylic acid derivatives as well. They are so because they can be hydrolyzed to carboxylic acids. And because a nitrile can also be hydrolyzed to a carboxylic acid, it's considered a carboxylic acid derivative. So let's look at an example first, and then we'll talk about the mechanism. So let's just say you have butane nitrile. And what I'm going to do is highlight the nitrile carbon so we can keep track of it. Conditions for hydrolysis are always acid and water. Remember, there's other ways to write that. You can write H3O plus. You could write H2SO4 and water. They all mean the same thing. Under these conditions, this gets hydrolyzed to a carboxylic acid. And the product you would get is this. There's the carbon that was part of the nitrile. It's now a carboxylic acid carbon. Let's look at the mechanism. So the first thing we do, we have our nitrile, and I'm going to abbreviate it with just an R group to keep it a little simpler for you to write. Don't forget that nitrogen has a lone pair. Let's draw it out fully. And in the presence of acid, that lone pair will get protonated, very similar to how a carbonyl oxygen gets protonated. So now we get the positively charged nitrogen. Now the water can come in. And this is a lot like the activated carbonyl. You have a carbon with a pi bonded to a positively charged atom. So now the water can add to the carbon, and we'll push a pi bond onto the nitrogen. Double bond NH. Now OH2 plus. Okay, the next thing, we'll keep this second step a little bit simpler and just do an intramolecular proton transfer. You can certainly do it over 2 steps if you want. So just when you do this, remember we're taking a bit of a shortcut here. We'll transfer the proton from the oxygen onto the nitrogen. So we get this. From here, we can draw a second resonance structure. And in this resonance structure, we just have a lone pair next to the pi bond. So I'll push that lone pair down, push the pi bond to the nitrogen. We get this structure. And now we need to get rid of the proton from the oxygen. So here I'll just be generic and use a B with a lone pair. That will take the proton. And I hope you all recognize this as the amide functional group. So this is a starting point. What happens from here is a mechanism we're going to learn in the next chapter. If you take an amide in the presence of acid and water, that will undergo an amide hydrolysis. And from there, what you end up with is your carboxylic acid, and then your amine comes off. Again, just keep this in mind. We will be learning this mechanism later on. The second thing we can do with nitriles is reduce them to give an amine product. So let's say we have this cyano group on a cyclohexane. And if you add LAH, lithium aluminum hydride, and then we'll just work the reaction up with dilute acid. Again, I'm going to highlight the nitrile carbon just to help you keep track of it. So this undergoes a reduction. To give the amine. So here's the nitrile carbon. Here's the nitrile nitrogen. And what you've done is you've added 2 hydrogen to the nitrogen. You've added 2 hydrogen to the carbon. And remember, a reduction can be classified as an increase in the number of carbon-hydrogen bonds, which is what we do here. So the mechanism for this, we can follow really what we learned before with LAH reductions. Because we're going to treat that CN pi bond a lot like we did a carbonyl pi bond. Just do a simple nitrile here. And if you take LAH, what we treat that as is a hydride source. So here's your hydride from LAH. That's a strong nucleophile. That will add to the nitrile carbon, pushing a lone pair onto the nitrogen. I should say a second lone pair onto the nitrogen. So we get a double bond, 2 lone pairs, a negative charge here. and a hydrogen. Then we still have this pi bond. And this next step, I'm oversimplifying it a little bit, but the way you can think about this actually happening is just another hydride coming in, attacking that carbon, pushing a third lone pair onto the nitrogen. Bit unusual, but we're going to draw two negative charges on the nitrogen. And we get this intermediate. In reality, we have this aluminum around that helps coordinate to the nitrogen, so it's not quite as bad as just two negative charges kind of nakedly existing on an atom like I'm showing it here. From there, when we do the acidic workup, just go ahead and write out 2 protons for us to use. We'll protonate and eliminate both of those negative charges just to get the amine. And that's your product. The third thing we can do with nitriles is adding a Grignard reagent to convert them into a ketone. And this is a really useful process. So let's take butane nitrile as our nitrile starting material. Again, for these reactions to help us keep track of things, I'm often writing in the carbon. That's not always going to be the case in your skeletal structure, so if it's helpful, just take the time to write your carbon in so you don't forget about it. And we can add any Grignard reagent. I'm just going to add phenylmagnesium bromide. And then follow that up with just an acidic workup. So what you end up doing is you add the R group from the Grignard reagent to the nitrile carbon. So we add the phenyl to that, and then that carbon becomes a carbonyl carbon. So we end up with a ketone product. Okay, so let's look at how this is occurring. So this is kind of reminiscent of the LAH reduction's first step, because what we're doing is we're taking a nucleophile and adding that to the nitrile carbon. Get N minus, the phenyl added. Now in this case, the Grignard reagent does not add twice like the hydride. So we stop here. And then when you add acid and water, the acid will protonate the nitrogen. And you have a functional group that you should remember as the amine. And you already learned what happens if you have an amine in the presence of acid and water. So we still have the acid and water floating around. We do the amine hydrolysis. So remember, take an amine with acid and water. That'll hydrolyze that to the ketone. Plus the amine. So if you need to review this portion of the mechanism, we talked about that in chapter 19.